Right, going to do a quick tutorial here on the activation of electrophiles, these super electrophiles for electrophilic aromatic substitution, EAS. There are essentially 6 ways to activate these super electrophiles, so 6 different types of super electrophiles. 6 types. I'm going to go through those 6 types in this tutorial. First up we're going to talk about is halogenation, and this is a way to make a bromine an electrophile. So normally we've seen Br2 be electrophilic, but when we're trying to react this with a benzene ring, right, this is all in the terms of electrophilic aromatic substitution. When the benzene ring needs to be the nucleophile, right, with a negative charge, or at least electron rich, not really have a negative charge, the benzene needs to be the nuke, we need our electrophiles to be really, really reactive because this is so stable. These pi bonds are very stable. So how do we make this even more reactive? We react Br2 with FeBr3. Iron's a metal, it's electron deficient. The bromines are going to interact with the metal. A lone pair on the bromine will go there. That will cause this to form. Now this bromine has a formal plus charge. The iron got electrons, it has a formal negative charge. And what happened here was now the bromine on the end is actually a good electrophile. This bromine, if I numbered them, bromine 1 versus bromine 2. Bromine 1 is actually an electrophile. So what will happen is the pi bond in the benzene ring will attack bromine 1, breaking the bromine-bromine bond. This gives a new product. The bromine is now bonded to one of the carbons, and the plus charge in the ring. Iron still has the negative charge, but you'll see at this point the substitution is going to take place where these electrons, right, even though the iron has a negative charge, the electron density is on the bromine. So any one of these bromines is actually going to be the one that takes the hydrogen and finishes the substitution. So it does elimination. First step is an addition step where we add the bromine. Then we do an elimination. So the first step was an addition. This is an elimination. And net overall, we're doing a substitution. The bromine has replaced a hydrogen on the ring. We made HBr. And we regenerated FeBr3. That is a catalyst in this case. The second type of super electrophile generation is for nitration. Nitration, where we're adding an NO2 to a benzene ring. So again, our benzene ring is our nucleophile, so we need to make this somehow into a super electrophile. So the way we do that, we take nitric acid. Make sure I balance my charges, plus charge there. And you actually react nitric acid with sulfuric acid. So sulfuric acid is more reactive acid than nitric. So in that case, nitric acid actually acts as a base, and sulfuric acid, of course, acts as an acid. So sulfuric acid, because it's a more reactive acid, is going to actually turn the nitric acid into a base. So it reacts, the nitric acid acting as a base. The oxygen lone pairs there react, essentially turning, right, you can imagine turning this alcohol into a good leaving group. Now it's a water leaving group. And also generated, right, the deprotonated sulfuric acid. What can happen here, this can collapse and kick out the water as a leaving group. And what that did, that just generated a super electrophile for us, because now it just generated this nitrogen that looks like this. And you can imagine that this is a very, very good electrophile, and actually it's electrophilic, most delta plus on the nitrogen. The other byproducts, of course, are water, right, and the O- from the conjugate base of the sulfuric acid. Then we take that, and that reacts with our benzene ring. Benzene ring is my nucleophile. Oops. Nucleophile is going to react with the nitrogen. It adds, forms the plus charge in the ring. Plus charge in the nitrogen. And overall plus charge, we need to balance that charge. Then also our sulfuric acid conjugate base can come back in and be regenerated by taking this H and doing that final elimination. And that gives us the benzene ring with the NO2 now on it. Make that nitrobenzene. We of course had water from before, and we've regenerated our catalyst, sulfuric acid. Net substitution, we exchanged an H on the ring for an NO2, making the super electrophile NO2. Third way we're going to add is we're going to add a super electrophile, do a sulfonation, adding SO3 to a ring, to an aromatic system. So to do that, we're going to take two sulfuric acids. One's going to act as an acid, one's going to act as a base. So this will act as a base, and it's going to take an H. So one's acting as an acid, one's acting as a base. That will have activated this, made that into a good leaving group. You can maybe see where we're going here. The electrons from the oxygen can come down, and that will kick out like a water. That will give us a sulfur that now is bonded to lots of oxygens. We have water, and we still have our O- from the first sulfur that got deprotonated. You can imagine this right here looks like a pretty darn good electrophile. So let's show how that works. Take a benzene ring and have it react with that. The sulfur here is going to be electron deficient. So pi bond from the benzene ring is going to react with that. That's the addition step, of course. We're adding this on. I would say we also, at the same time this comes in, this breaks that bond, so it's an addition. So there's an OH here now, plus charge here. Again, we gotta do that elimination to finally get rid of that H to finish the substitution. And regenerate the sulfuric acid. Takes that H, finishes that, does an elimination. Sorry, up above, I should have said HSO3. Is what we end up adding. There's an H there too. What's our final product? SO3H through our net substitution. So the activation of this super electrophile, create that super electrophile to add the sulfon, the SO3H. Next type of generation of super electrophile is called the Friedelcrafts And what we do here is we add an sp3 hybridized carbon to an aromatic system. So here's an example to generate the super electrophile. So you have a chlorine bound to a carbon. It's going to interact with aluminum trichloride. And you can imagine this aluminum is again very electron deficient. So it's very similar to the FeBr3 as we saw before with Br2. It goes there. This will create a chlorine with a plus charge now, the aluminum with a minus charge, given the electron density is still on those chlorines. And what happens here at this point is essentially the carbon-chlorine bond is going to break. So the carbon-chlorine bond is going to break. This is going to, of course, generate a carbocation, which we know is going to be a great electrophile because it's a carbon that's electron deficient that doesn't have a full octet. And it generates this aluminum now, the negative charge, bind to 4 chlorines, but all that electron density is really on the chlorines. So how's this going to react with an aromatic ring? Here's an aromatic ring. Of course, the aromatic ring is the nucleophile. The pi bond is the aromatic ring is the nucleophile. Pi bond reacts with the carbocation. That will generate a plus charge. And now our aluminum comes back in. That have all those chlorines bonded to it. And the chlorines, of course, have all that electron density. So aluminum chlorine bond breaks. It's going to take the H that ends up needs to be substituted to form that new pi bond, which of course recreates the aromatic system. And the final product is we've replaced an H with an sp3 hybridized carbon. We generated HCl, and we regenerated AlCl3, which is a catalyst. This works really, really well for tertiary alkyl halides and secondary alkyl halides, or any of the benzylic or allylic alkyl halides. It works really well for those. The thing about you had to generate carbocations, you had to make a stable carbocation. So remember your carbocation stability rules. I would also add here that it has to be, this is important, sp3 hybridized. Things like this or vinyl will not work for this. It has to be an sp3 hybridized carbon. Alright, our next one is called Friedelcrafts acylation. This is adding a ketone to a benzene ring. So we need to do here, we're going to have a acid chloride, is what this is called. An acid chloride. Acid chloride. The acid chloride is going to, again, the chlorine is going to react with the aluminum. Very similar to Friedelcrafts acylation. You're going to need a chlorine with a plus charge, aluminum with a minus charge. And now, the oxygen lone pair is actually going to kick down and kick out that chlorine. What's that going to do? That's going to generate this acylium ion. There's a plus charge on the oxygen, where this carbon is very, very electrophilic, very, very delta plus. It's a acylium ion. These do not rearrange. Friedelcrafts acylations, no rearrangements. But now Friedelcrafts alkylations that made that carbocation one before, those will rearrange because they make carbocations. These will not rearrange. So the other thing we make here is, of course, the aluminum with the 4 chlorines on it, so a negative charge. So we've got our super electrophile. Now let's see how it reacts with our benzene ring. Our aromatic ring. So we have our aromatic ring, which is the nucleophile. The carbon that's bonded to the oxygen is delta plus. Electrons go up. We're adding it in here. Plus charge on this carbon. Our AlCl4 comes in. Very similar to what it did in the Friedelcrafts alkylation. We're going to take this H, chlorine can break, make that new pi bond. It's going to give us the newly substituted benzene ring. plus HCl and AlCl3. The catalyst has been regenerated as a catalyst. Very good. The final is carbocation. It's an old friend of ours, of course. In this case, we're going to generate a carbocation. It's going to add an sp3 hybridized carbon to the benzene ring, and again, sp3 hybridized. So one of our first reactions we learned, pi bond attacks. We generate the more stable carbocation here from between carbon 1 and 2. Carbon 2 will be more stable, more substituted. We gotta be careful though, because carbon 2 we can do a hydride shift. Remember, we have carbocations. Carbocations will rearrange always. So Friedelcrafsalkylation and carbocations always rearrange, because Friedelcraftssalkylations make carbocations. Carbocation rearranges. What's that make? One from a secondary carbocation to a tertiary carbocation. Now this can react with the benzene ring. Carbocations, of course, are great electrophiles. Draw our benzene ring. Draw our carbocation that we've rearranged, gives the most stable carbocation. Pi bond reacts. Here. Make sure we don't screw this up. There's a plus charge right there. And then to regenerate this, the H just actually falls off. The H plus just falls off. Because that will make the final substituted product plus H plus, which we started with, which is a catalyst. I will always tell you if something's a catalyst. Be careful for those rearrangements.